Okay. All right. Has anybody published a paper yet? Did any of the research and published a paper? It's okay. You don't. Someday you may. Proofread your papers, if you ever do. Because this actually got into a paper that went into a journal, and some guy found it and put it on Twitter. Of course. And you really don't want your competitors, well, maybe your competitors, but you don't want people that you might someday want to collaborate with seeing this written in your paper about them. Yeah, not a good thing. Not a good thing. Always make your side comments in red, something like that, so that it comes out right. Okay, so we're going to kick off today talking about an interesting data structure that is it could be an entire semester-long class in itself. Okay, this idea of graphs, and we'll talk about what graphs actually are as we go along. But from the standpoint of how deep are we going to go into graphs, we're going to go this far into graphs, and it's this big, right? It's a huge topic. But we'll get the big stuff out of the way, and you'll if you are more interested in it, you can go on and study that. It gets really mathy pretty fast, as it turns out. But it's a kind of a neat topic. All right, before I get going into that, does anyone have any questions on homework 5, on grading, on anything else related to the class? Yes?
When do we plan to sign up for time to meet with the TA?
Yeah, good question. So as I said, homework 5 is going to be in-person grading. I will try to set it up this weekend because it's due Friday, and then I'll try to set it up this weekend so then Monday we'll start knocking those out. There should be plenty of time. I'm not super worried if it takes a week or week and a half to do it. I'd like to get them all done before Thanksgiving if we could. If it slips a little, I'm not too worried about it, but that's more for you trying to arrange times to meet. Okay. The grading itself will be it'll be laid out, and you'll see how we actually do the testing, and then you'll go in and you'll have to describe what your program's doing, why it's doing this, and so forth. Okay. It's not hard, and in fact, I think people last year did the same thing, got a fair amount out of it. So I think that'll be good. All right. Any other questions? Homework is due Friday, and I'm going to be very strict about any extensions because you had plenty of time to work on this one. All right. And the next one is going to come out Sunday, so we're going to talk about it Monday. So I don't want too many lingerers.
Will that be due before or after?
Oh, it'll be due the last day of classes. It's 3 weeks. It's that long. The final project, yeah, yeah. You've got time, but it's enough time. Let me put it that way. It's a hard project, but it's enough time if you work on it. If you spend all day Thanksgiving working on it, it'll be fine. No, I'm just kidding.
Only on Thanksgiving.
Yeah, just Thanksgiving. You could probably do it all just on Thanksgiving. There you go. Okay. All right. So here's what we're going to do. We're going to talk about graphs. Then at the end, I'll show you a little graph software that will, if you want to play around with, you can download it. I haven't figured out a couple things about it. I just found this software a couple days ago. Haven't figured out everything about it yet, but it seems like it's kind of interesting in the way it runs. So I'll show you that. All right. So when we talk about graphs in computer science, we mean the picture on the left, not the picture on the right. Okay? This kind of graph or chart or whatever is totally different than the specific graph we're talking about for computer science. Does that graph remind anybody of any structures we've used so far? Trees, right? I mean, it looks kind of like a mangled tree. If you took a tree and you went and played around with everything, but there's crazy issues about it too. There's no parent of or rather, it looks like 9 has 2 parents, which I suppose would be real life, right? But some of these are weird. There's no structure to a computer science graph, and I like to call it the Wild West, right? Because it's there's no structure to it, and you have to think about it in a different mentality than a lot of the other data structures we've talked about. Okay, we will be able to put a structure to it when we actually create a data structure that holds graphs. but it's definitely not a nice like linear or logarithmic sort of thing. It's a little bit wackier there. Okay. So here's what a graph actually is. So it's a data structure, obviously, and really common, nonlinear. It consists of these things called vertices, okay? And I don't know why I put links. They're not really called links. They're called edges in this case, but there's no structure. Okay, so we'll see what this is. This is the simplest type of graph. It's called an undirected graph. Okay, the difference between this, notice the difference between this one and this one. Besides the numbers, what's the difference? No arrows, right? What this really is with a graph, we talk about a bunch of vertices and a bunch of edges connecting the vertices. Okay, so we can actually write that. Any blue chalk? Nope, no more blue chalk. I don't see any. We can talk about the edges and the vertices being like a pair from a vertex 1 to a vertex 1 to a vertex 2, and that defines like the edge between the two, right? Between v1 and v2, there's some edge that connects the two. Okay? And the pattern, like the actual structure, who knows about it, right? Like this one connects to these two, but then this one connects to these two, and this one connects all the way around, and there's no real structure. But this is an undirected graph. Okay? Those are called the vertices. Singular is vertex. And the edges just connect them. Okay? Many times we will label them. We'll label both the vertices with either some sort of label that talks about a number, like so you can number them pretty easily, excuse me, or just a letter or whatever. And then many times we label the edges as well. And later in the lecture we'll talk about the edges having what we call weights on them. So we actually put a number there that tells you how much it, quote, costs to go from one to the other. Okay, and we'll talk about all the sorts of details about that coming up. Okay. What's kind of interesting and a little frustrating about graphs is that because the structure is so non-determined, those two graphs happen to be the exact same graph, right? And if we broke it down into into the edges, like for instance, v0 and v4 are connected in this one, and v0 and v4 are up there. That's the edge, right? v3 and v2, the same with v3 and v2 here. So if you look, and unless I screwed something up, all the edges and all the vertices line up. These are the exact same graphs, even though they look completely different. Okay? That's just because the structure isn't well defined for a graph. Okay? Let's take an example. Let's look at an example of a graph using a fun little game. Well, it's kind of a silly little game. But who was playing the super tic-tac-toe the other day? So yeah, you guys were playing that. I was thinking about coming up with, you could probably come up with a graph for tic-tac-toe as well. It'd be a much more like broad one. And then the other, I talked about it in the other class. I talked about you guys playing this in the other class. And they, not specifically, they have no idea too. But I talked about it, and some people were like blown away. They're like, holy cow, that's the most amazing game. So, hey, it's kind of neat. Here's a game we're going to play, OK? It's going to be called, I just call it the coin game. And what you've got is you've got a head and a tail and a head. And what we've got on here is we are trying to go from heads, tails, heads to tails, heads, tails by following some rules, because it's a game, right? And the rules are as follows. You can flip the middle coin at any time. OK? You can flip an end coin only if the other two coins are the same as each other. Right? So right now, the only one we could flip is the middle one because the two ends are different. You can't flip an end unless the other two are the same. Everybody get it? OK? So what we're going to do is we're going to come up with a graph of these. So first things first, how many states are there? How many different ways can we arrange three coins like this? I heard it. Alice, why 8?
Because there are two choices for each of the three slots.
Yeah, there's two. This is a combinatorics problem, right? Anybody taking discrete math right now? Right? Yeah, if you're in discrete math, and you know that if there's 2 selections for this one, and 2 for this one, and 2 for this one, you've got a total of 8 total states that this could come into. Okay? And what we're going to do is we're going to enumerate all those states. In other words, all 8 of them, we're going to connect them by these edges. We're going to create a vertex. Like this would be one vertex, right? This whole state is one vertex, a head, tail, head. Okay? And the next state is going to be whatever states this can go to. Okay? And then we're going to connect it with an edge. All right? Here's what I want you to do. Try to do that. Try to make yourself a little graph. There's going to be 8 of these, right? Connect them together, and let's see how you do. Okay? Take the next like 5 or 6 minutes. Work with your neighbor or whatever. Try to do it, and we'll see how well you do. If you don't understand it, that's OK. But basically, we're writing down heads, tails, heads, and then tails, heads, tails, and tails, 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 and tails, heads, heads, and all 8 states. And we're trying to connect lines by which state can go to which one. Make sense? Wow, you whipped that out pretty quick. How's that? What do you have here? So there's where you start? And where do you finish? How many flips will it take to get to your finish?
5.
So 1, 2, 3, 4, 5. Oh, I like that. Okay, and you got the same similar sort of graph?
Well, I realized that I didn't really have a strategy, so I decided that it was like, wow.
Okay, no, that's pretty good though. But you basically have the same. You have 8 things here, right? 1, 2, 3,
Well,
4,
I
5,
haven't-
6.
I'm not
No, you didn't finish it.
I'm not
Put the
done.
other 2 states in.
All right,
Right, fine. Oh, yeah.
Okay. Did you guys figure out?
Yeah, it's up there. Pretty little chart.
Let me see. Oh, whoa, look at that graph.
Different colors and everything. Look at
Different
it go.
colors and everything, yeah. So arranging your graph is an interesting part. Okay, I like where you started. Okay, you're getting there. I like the fact that you got links. How about you?
So I found the answer, but then now I'm trying to do the graph.
Now you're trying to do the graph. Yeah, building these graphs is not it's not the easiest thing in the world if you haven't done it before. All right. I saw a whole bunch of good ones. Is people still working on these? Okay, I saw a whole bunch of good graphs. Question. What can I go to? What did we decide the next thing we can go to here is? Okay, so that's probably not a bad thing to write next, right? So I know a lot of you guys just wrote down all the ones, but isn't there going to be a link between those two? So if this is one vertex and this is another vertex, you can go there, right? Okay, how many different ways can we modify this one? What's one of them? Okay, so we'll flip the left H. That would be tails, heads, heads, or flip the right H, right? Right? And then you've got heads, heads, tails. 1, 2, 3. We've got half of them already done. Woohoo. OK, how about this one? What can we do? We could do, you can only do one, well, you can do what? You can flip the middle, because you can always flip the middle, right? But you can't, and you can flip this, and you can't flip this one, though, right? So if we flip this one, where do we go? Back up here. So we already did that one. So let's do another one here, where we flip the middle one. Tails, tails, heads. Is there an equivalent one we can do over here? Yeah, sure, right? That's going to be heads, tails, tails. We're almost there, right? What can we do to this one? You can flip the middle again, or you can only flip this one, right? And if you do that, it gets tails, tails, tails. What if we flip this one? Tails, tails, tails. Tails, tails, tails. Boop. OK. And then what can we do to this one? We can flip the ends, which we did, and we could go to either one of those ones. Or we can flip the middle. And if we flip the middle, we end up with tails, heads, tails. And haven't we won the game? Right? That's where the and then we've got all the states in there. And now this is our nice little graph. Right?
This would be non-directional, right?
This is not directional, right? And why is it not directional? Can you always go between positions? That's the neat thing about this game. You can always go in positions. OK, so now that we've got this up there, what's the best you can do in terms of winning this game? Cecily, you told me earlier. What was it? 5 times, right? If you start here, you got to go 1, and then you got a choice. Either way, 2, 3, 4, 5, and you've won. And that's the best you can do. Are there worst ways you can do it? What's the worst you could do? Infinite, right? 1, 2, 3, 4, 5, 6, right? You could go, or you could go bing, 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 bing. I mean, it's because this is undirected, you're definitely in a position where you could go, it could be an infinite number of tries, right? And if you're like 6 and trying this, it might take that long, right? But hopefully as 19 or 20-year-olds, you could have done it in less than like 10 tries. Yes, Rana.
There's no way to get there by doing all of them?
There's no way to get there by doing all. Sure, you could do all of them and get there. You mean you hit all the states?
Hit all of them once.
Oh, hit all the states once. I don't think so. No, you're going to be in trouble trying to hit all the states once, because the minute you go one way or the other, you're done. Right? No, yeah, you're done in that case. But yeah, you can. I mean, you can get here, but you can not hit those two and still do it. Yeah, yeah. OK, so good job, right? But that's the graph, and this is exactly what we came up with, I believe. Heads, yeah, same exact one. OK, and I saw a whole bunch of crazy-looking graphs out there, right? Which is fine. First time you've ever drawn these, it's tough. But try to do it in kind of a like an organized fashion, and you end up getting a graph that makes sense. But if you just write down all the cases and then try to do the edges to all of them, you'll get a little crazy. But you'll still have the same graph. I mean, like I looked at a couple graphs that are literally the same graph as this. It just the lines are all over the place, right? But that's the way it goes. OK? All right, so that's an undirected graph. OK, we did this, 1, 2, 3, 4, 5. And there we go. The other graph is a directed graph. These are sometimes called digraphs. I don't think there's an equivalent term for an undirected graph. You just call it a graph, because most graphs are actually undirected, as it turns out. But in a directed graph, you can say, look, this one can go to this one, but you can't go the other way. Like there's no way to get from this one directly back to this one. You might have to go all the way around to get there, right? If you start at this one, can you ever get to this one? No, it's not even available to you to get there, right? You have to start at this one if you're going to get to all the other ones. OK, so directed graphs are they're interesting in that they allow some different type of behavior from your graphs. OK. Graphs can actually have loops, where a graph loops around and it connects to itself, right? We would write that in the ordered pair like this. We would write v comma v, and that's allowed. It just means that the graph connects to itself through some path. Why would you want to do that? Well, it depends on what you're talking about. I put this up here. Graphs can have multiple edges where 2 edges are in the same direction. I just looked it up like before I came to class, and I don't think that's actually true. I don't think you can actually have two of the exact. I don't think it makes it, like, those are really equivalent cases. Although there might be a case where in some cases I can see why you might want this. Okay? Let's pretend you're Google Maps. Okay, let's pretend you're Google Maps and you're trying to get directions from Boston to New York City, right? Has anybody ever driven from Boston to New York City? Yeah, you can go like 4 different ways. And depending on which way you go, you could be sitting in traffic for a long time. If you try to just go, oh, 95 will take me there, you'll end up in Providence, and you'll end up just getting Connecticut. You'll get hit by lots and lots of traffic, right? If you go west for a while, out 90, and then down, what is it, 91 or 80? 91, I think it is. You'll get there much faster, right? In most cases, but then there could be like a snowstorm or who knows. But if you're Google, and you might have 2 different roads going between 2 different cities, or 2 cities that have different properties, right? And maybe you want to implement them a graph that says, hey, there are distinct things here. Like one might be a highway and one might be a local road or something. So you might want something like this. But I guess in many cases you won't see that. But in some graphs you might. Anyway, I looked it up and it said, no, it's not allowed. But then I thought of some examples. So I don't know. OK. How do we actually represent these graphs? Now remember, visually, graphs can look like lots of different stuff. You all had 20 different versions of our little game here in your own graphs. But when you if you take a graph and you turn it into in the actual data structure, they all should converge to the same value. This method is called an adjacency matrix. What it means is you put all the vertices down one side like this. You put the same vertices up at the top, and you say, well, if there's a path for a directed graph, if there's a path from the row to the column, you put a true. And if there's not a path, you put a false. Okay? So let's see if I did this one right. So for 1, in this case, 1 has what we say is they're adjacent. 1 is adjacent to 2, and it's going to 2. So we have a true in that column. And then 1 is adjacent to 3 as well, and 1 is adjacent to 4. But it's not adjacent to any of the others. OK? And as far as does anything point to 1? No. So down here, you'll look at this. There's nobody true pointing to 1. So unless you start at 1, right, you can't get to 1 in this graph. OK? What's the issue with an adjacency matrix? What do you think, Josh? Space. Yeah, it's huge, right? Notice that there's a very few number of trues in here, and this still looks like a pretty complicated graph, right? It's not totally complicated, but it's not what we call I forgot the word. Not a complete graph. I'll have to look it up. I forget what the actual word is. But if you try to connect all the edges to all the other edges and fill this up, this thing would look crazy, right? Most of the time, that's not the case. OK, like a fully connected graph or whatever. Not the case, right? And in fact, even if all of these went to the others, what would still be false in this one? Going to the self, right? Yeah, this line right here would be all falses still, as it turns out. OK? Now you could have, if you wanted to make it even more connected, you could have 1 loop to 1 and 3 loop to 3, and then you could fill the whole thing in. But yeah, so space is not a good thing. If v is the number of vertices, how much space does this adjacency matrix take up? V squared, right? So that's not necessarily the best. What is nice about this is it provides constant lookup. If you want to know if there's a directed edge from 4 to 6, you go to 4, you go to 6, and there it is. That's constant lookup. You don't need to look through all these to do that. OK? So the trade-off to the constant lookup is lots and lots of space. OK? If this was an undirected graph, OK, what would be interesting about this was every time you saw 1 to 2, you'd also have a 2 to 1. And what would be interesting about the matrix? It'd be symmetric about what? Kind of about the diagonal, right? In fact, if you wanted to, and it was an undirected graph, you could save space by just going like here and saving everything below this kind of line that I'm doing. All of that is mirrored on the other side. And so you could save space by doing that if you wanted to. But that's only for an undirected graph. OK? All right. Yes, question?
Well, assuming
Uh-huh.
would you just allocate that memory below that?
Yeah, that's a good question. You'd have to figure something else out about it. Like you'd have to figure out, okay, I'm going to compress this somehow and know that I do a translation of some sort. It's not trivial, I think. Yeah, Alice?
Could you do the space over the diagonal and then have an array of like 1, 2?
Oh, could you do the space? You could do the space over the diagonal, and then maybe it'd be easier to. I mean, it's kind of the same idea, though, right? Either way, you're gonna have a nice linear one here, and then like staggered somewhere else, and something else can be staggered. But yeah, it's not trivial. But I'm sure you could figure it out with a little bit of thought if you really wanted to do it this way. Okay. Can anyone think of a different way to represent this? Max, what do you think? A set of vertices and a set of edges. So 1, 2, 3, 4, 5, 6, 7. There's your set of vertices, right? 1 is going to have what set of edges associated with it?
1, 2, 1, 3, 1, 4.
Yeah, how about just 2, 3, and 4? We don't even worry about the ones that are false. That's an even better way, right? So you don't even need to worry about the ones that are false. This, and maybe that wasn't exactly what you were talking about, but this would be called an adjacency list. Notice how much smaller it is for this same graph, right? You've got vertex 1 connects to 2, 3, 4. Vertex 2 connects to 4, 5. 3 goes to 6, right? You only need on the order of the number of edges plus the number of vertices for this representation. Much less space required, especially if you've got what we call a sparse graph, which means not so many connections. And even though this graph looks like there's a ton of connections, it's not that many. Because think about how many more 5 could go to, right? It could go to 2, it could go to 1, it could go to 3, it could go to 6, right? So I mean, all of those, like the amount of extra edges that we don't have represented over here is huge. And when I say lookup is order n, what is that all about? Let's say I want to say, hey, does 4 connect to 3? What do I have to do? Yeah? Go to 4. And you have to search, bing, 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 and see which one. So some sort of linear search here, right? Or maybe you could do a binary search if you really wanted to. But I mean, it's some sort of search in here where there's an extra amount of searching. You don't get that constant lookup. But this isn't a bad way to do it. Okay? Not a bad way to represent it. And definitely, if you have sparse graphs, it's a good way to go. Okay? Yeah, Josh.
So say you have like 3 connecting to 4. Would you okay, let me rephrase. Do you put the like which one of the vertices are you going to put in that table?
Oh yeah, okay. This is the one that it's coming from. These are the ones it's going to. Okay? Just like in the previous one, right? These are the ones that are coming from. And these are the ones that are going to.
Okay.
Make sense? Yeah, sorry for that being confusing. Yeah?
If you want to see which ones are going to the vertex, it's going to be.
Oh yeah, if you want to see which ones are going to a vertex, you're going to have to look through the whole thing, aren't you? Right? I mean, if which ones are coming from, no, which ones are going to 6, right? Which ones go to 6? Well, you got to look through that one. Nope. Nope. Yep, there's one, there's one, there's one. Yeah, so it's a little more intense doing that too. Yeah, so you have to do that. But as I said, this is one way to do it. Not a terrible way if you want to conserve some space over the n squared or v squared you would have before. Yeah, Natasha.
I don't really understand how it's O n if you needed to see 4 connected to 6.
Sure. Well, that's worst case, right?
Okay.
So I mean, you could say just have 4 connected to everybody. And then if everybody was connected to everybody, you'd have to look through all the, you'd have to go to 1 and look through all the way up to v edges there. Yeah, so it's worst case. Yeah. OK. All right. So let's see. You can, of course, store these in a hash table if you want, right? You've got the keys, which are the vertices, and the edges, which are the lists, which is kind of nice if you wanted to do it that way. Why not? We know about hash tables now. OK. We can also, and this gets a little more complicated. It just keeps like adding a couple levels of complication here, right? We can also represent the graphs with these weighted edges, or weighted paths, if you want to call them that. All right. What's that all about? Well, that says, hey, it takes me, quote, 2, whatever 2 represents, to go from vertex 1 to vertex 2. And it takes 4 to go from vertex 4 to vertex 7. Now, what could those weights represent? What's that? Sorry? Oh, minutes. Yeah, travel time. So if you're talking about Google Maps, right? Google does this all the time, right? What are the things that Google Maps uses to determine how long it's going to take or which route to give you? What's that? Traffic. Else? Distance. Average speed, right? Whether or not there's like policemen who are going to pull you over, I don't know. I mean, who knows, right? Google's got their own secret formulas for this. But the point is they're using lots of different data, and their weights here are going to be based on a whole bunch of different things and probably change during the day, right? I've been using Google Maps to go places like the live one on my phone, and in the middle of the route, it's changed. It's been like, take the next exit because there's an accident or whatever, right? So they actually update it in real time. How do they do that? Well, they've got, people can actually report accidents, or they're just looking at your phone, looking at other people's Google or Android phones and saying, these people haven't moved in a long time. There's probably something going on there, right? Traffic. So that's how they put the little red traffic lines and all that too. But interesting stuff, right? So anyway, so what we can do with these weighted edges is we can say, hey, what's the cost to go from one vertex to some other vertex? And it's really easy to do. It's just a matter of addition, right? So to go from 1 to 4 to 7, right, has a path length of 1 plus 4, or 5. Okay? If this was an unweighted graph, all of these would be 1. The 1s are implied, right? So an unweighted graph, to go from 1 to 7 is just 1 and 1. It's just 2. There's 3 vertices, and there's only 2 jumps you need to make. But if you have weighted ones, you just add them together. Okay? So what might be an interesting thing that Google definitely thinks about from going to, say, vertex 1 to vertex 6? Yeah, Alan.
Route optimizing.
What do you mean by optimizing?
Because there are many paths to get from, also paths to get from 1 to 6.
There are many paths. In fact, I would wager that there's an infinite number of paths, because you could always go, there, there, or you could go like there, or you could go there. Well, there might not be an infinite one. You can't get back to 1. You're right. So you can't get back. So there's not an infinite number. But the point is, there's lots of them, and you definitely want to find some optimization. But you still haven't defined optimization for me. OK. The cheapest, or the least, or the shortest is what we normally call it. OK, in this case. So what we're going to spend some time on is trying to figure out the shortest path for various graphs. OK, and it's kind of a neat, it's actually one of the things we'll talk about at the end of class today is probably the most famous equation algorithm in all of computer science. OK, and it's based on finding the shortest path lengths. OK, all right. Right now, what's the shortest path from v1 to v6? Figure it out. Some people already did, I guess, but v1 to v6. What do you think? Who hasn't answered in a little while? What do you think? Yeah, go ahead, Dinesh. 1, 4, 7, 6. So what's the path length? 6, right? So Dinesh says, hey, go from here to here. That's a path of 1. That's 1. And then 5 when you add the 4, and then 6 to get here, right? And that happens to be the minimum, right? If you go this way, it's actually 9. If you tried to go this way, it's also 9. If you were crazy and went this way, it'd be like 2 and 3, 5, and then 8 would be 13. But how did you figure that out? Yeah, you used your mammalian brain and saw patterns and figured it out, right? You humans are actually pretty good at this. Not necessarily this level of detail, but humans are actually pretty good at going, OK, I can look at that, and OK, it's not going to be over there because the 10 is there, and you narrow it down pretty quickly, right? You narrowed it down pretty quickly. But you did do what we call an exhaustive search, more or less, right? I mean, you had to at least consider these guys over here, and you had to consider, some of these over here. So you probably did some sort of exhaustive search. Well, the question is, can we make an algorithm out of it? Of course we can, right? There's definitely going to be an algorithm out of it. Although it's not a trivial algorithm, especially for the one with weighted graphs or with weighted paths. But we'll get there. OK, we will get there. All right. Finding the shortest path. If you look at flight paths, right? Unless you can get a direct flight, there might be 2 or 3 different ways of getting from A to B. And in fact, well, in general, well, not necessarily. Sometimes the direct flight is not the short, or not the one that's going to get you there soonest, right? Let's say you want to fly on Tuesday, right? And there's one direct flight, and it's at 6 p.m. Well, if you take a non-direct flight at 10 a.m., you might get there quicker, even though you spend more time in the air and go many more miles and whatever. But normally you're not talking about like starting times or whatever in terms of these sorts of graphs. But the point is that mapping, things like flight distances and so forth, all these things are graph related. You think there's any programs you guys might use, or like services you might use that have graphs? I phrased that specifically, like I meant to obscure it a bit. Yeah. Facebook. Facebook's a huge graph, right? And trust me, they mine it for everything they can, right? Like here's Sally, and she's connected to Bob, and Bob's connected to Joanne, and Joanne's connected to Sally through there. And I mean, it's one huge graph, right? And they can figure everything out about it. In fact, Professor Ben Hescott, who works here, does a lot of work on graphs. This is like his bread and butter. He does a lot of work on graphs, specifically with Facebook, to try to figure out stuff that Facebook doesn't even know, based on anonymous graphs, right? Like you can tell just by like graphs lots of kind of interesting things about people, and that they might not know based on like their friends and their other things, right? I mean, if you know something about a bunch of people, and then you know one other person that like drops into that group, you might know something about that person too, right? And because the graph's so huge, it gets kind of interesting. Okay? So anyway, so we're going to find out the least paths. Yes? Ganesh. Neural networks are graphs in general. Yeah, it's very similar. Now, I mean, I don't know much about neural networks, but they model it with graphs many times. Yeah, so I would say neural networks uses graphs to get there, like to analyze their behavior. Yeah, or any kind of network or whatever else you want to talk about too. I mean, networks are very big like this too. Yeah.
But edges don't always have to have values, right?
Edges do not have to have values. No, if it's an undirected graph, they've all by default got a value of 1.
Okay.
Yep. Right. Okay. So we already did this. Shortest path was 6. Notice that there's no path from 6 to 1. Can't get back there. Right? You can't go back. Okay. Some graphs, this will blow your mind, some graphs have negative weights. Right? It's like the wormhole graph or something. Right? These negative weights cause you problems when you're trying to do a shortest path. Because let's say you were trying to go from 5 to 4. All right. Your path is 1. Right? But what if you go 5 to 4 to 2, then your path is 4, but then you go back to 5, and now your path is -6, and then you go back to 1, or back to 4 rather, and your path is -5. So to get from 5 to 4 is -5, not 1. And what if you kept going around? It'd actually be, what, -11 or something, right? So you can keep going over and over again. So for a graph with negative values, you can get these things called negative cost cycles, and there is no shortest path because you can keep getting shorter, even though shorter in negative numbers is kind of weird. Like, what's -7 inches? It doesn't really mean anything, right? But you have to be careful about that. If you see graphs that have negative weights, you have to go, oh, can I figure things out about this? Turns out you can. We'll do that on Monday, but we have to be careful about it in this case. Okay. All right. So let's do this. Let's find the shortest path algorithm for an unweighted graph, not where the default weights are all 1. Okay? What you do is you start and you say, OK, we want to find the shortest path from some vertex. We're going to call it S to other vertices. And you pick the first one. So basically you're saying from one of these, what's the shortest path to all of them? Okay? And then we figure it out. Okay? So if we pick 3, all right, let's pick 3. And the path from 3 to 3 is how much? 0, right? You're there, right? It's like saying, And when you're at home telling Siri to take me home, right? Siri's kind of snark, and she's like, you are home, or whatever, right? But that's it. So 0 is where the path length from the start to itself. Okay? All right. What you then do is you say, OK, let's look at the ones that one goes from, or the vertices that are adjacent to the one you started at. In this case, 1 and 6. And how do we know what the distance to 1 is? Yeah, we already said that the distance between 2 is 1. And if it starts at 0 and there's one more, it's just 1. OK, what's the next one we can look at? Yeah, 2. You could look at. Let's see. I guess you could. Well, you could look at. We basically look at 1. That's what I mean by looking at it. You look at 1 or look at 6. And you can pick either one. It doesn't actually matter. But if we look at 1, then we go, OK, 1 is adjacent to 2, and it's adjacent to 4. And therefore, what's the distance to 2? 2, and the distance to 4? So we just add 1, right? You just add 1 to whatever this one is. Then you look at 6, and you go, oh, nobody loves 6. Or I guess 6 doesn't love anybody, right? And you say, fine, we're done with that. OK. And then that's 6. So no vertices from 6 to anybody else. And then you just keep doing the algorithm, right? You go from 2. Then you look at 3, right? And you go, OK, so now 3. Let's see. We went from 4 already, so it doesn't. Oh, sorry. We look for a distance of 3, rather. Right. So you look for a distance of 3. So 2, there's a distance of 3. And there's also a distance of 3 from 4. Right? OK. And we're done. Right? And by the way, if we disregard any paths that are shorter than the one that we would become. So for instance, to go from 1 to 2, we're at 2 now. 2 is adjacent to 4. But why don't we make this 3? It's already less, right? It's already less. It's 2. So we don't need to make it 3. OK? And here we are. We're done. This is called a breadth-first search. OK? A breadth-first search is very similar to a level-order tree search. In other words, going by level, 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 level in a tree. OK? And so you can do this very similar. You can have a very similar algorithm to doing a level-first search. Now, how do we actually do this algorithmically? Right? How do we turn it into code? Well, we have to represent it somehow. So here's how we represent it. We just say, fine, here's a table. There's all the vertices down here. What we do is we say that a vertex is known when we have handled it and we've taken care of anything that it's adjacent to. In other words, going from it. OK? So right now, what we do is we start out and we say, OK, vertex 3, that's the one we're starting at. We already know the distance is 0. We haven't done anything with it yet, so it's still unsolved. The distance to all the other ones, as far as we know, is infinity. Could it be that we get through this whole thing and there still remain some infinities? Sure, right? If nobody had any vertices going into it, that would end up still being infinity, right? OK. So all you do is you process these based on the order of what's next in that you've already handled. Basically, once you get numbers here, you start working on them, and you set all non-efficient infinity ones to the distance that you're at plus 1, and that's it. So it's not so hard, really, right? So let's walk through this. No, we won't walk through this. We'll look at the actual code. You don't need to worry about this code necessarily. I'm just kind of recognize it and see what's going on. Basically, what you're doing is, this is pseudocode for what it's worth. For every vertex, basically, if it's an unknown vertex, right, and the distance is the current distance, you're going to make it be known now, and you're going to handle all the different adjacent vertices to the one that you're at. That's it. It's exactly what we were doing. OK? Problem with this code is that it's an order v squared algorithm, because it basically has to go through all the nodes, or all the vertexes, and go through all of the other edges and see if they're connected. And it's not so good when you get a nice degenerate graph like this, right? It takes a long time to do this algorithm. OK. So let's just walk through this one. I won't belabor the point, but we'll walk through it. if you start at vertex 3, and it's the exact same example we just said. If you start at 3, you've got nobody is known, and you've got a distance of 0. Then you look at the vertices that are adjacent to vertex 3, and you set them equal to 1 plus the current, which is 0. So they're 1 and 3. OK? And you set that one. You set vertex 3 to be known, to be true. OK? Then you do the same thing with 1. You can either pick 1 or the other. It doesn't actually matter. Do the same thing with 1. 1 connects to both 2 and 4. So 2 is going to be 1 more than 1, and 4 is going to be 1 more than 1. Same thing. And then you do 6, which we don't have anything to do, because nobody's adjacent to 6, going out of 6. So you just set it to true. And then let's see, you do 2. And the only one that we're going to worry about is 5, because 4 is actually less already. So you can look at it and you go, oh, is it less? Yeah, don't worry about it. Right? But for 5, you have to increase. I think that was infinity before. Okay. And then you keep going, and you have 4. And 4 goes to a whole bunch of things. Goes to 5, which we don't need to change. And it goes to 7, which we did need to change because it was infinity. And then it goes to 6, which we didn't need to change because it was already 1. And then you've still got to take care of 5 and 7, but everybody's already completed, so you don't actually have to do anything with those. OK? Yes, Alice. What do you use for infinity? Good question. Depends on what your data structure is. You could use a true false and say it's infinity or not, or you could say it's, or you could use like max int or whatever if you're doing that. Yeah. So it depends on the way you're implementing it, but yeah. Actually, some programming languages have an infinity number you can use that's designated as infinity. Kind of nice too. OK, questions on that algorithm? Can we do better than that? Like that algorithm was at v squared. Anybody remember how we processed level order trees? How did we do that in that? We did a lab on that. I remember how we did it. It was the same lab where we used stacks. We used a stack and a queue. You can do that with a queue. What you basically do is you take a vertex that hasn't been seen yet. You put it in the queue. You pop the queue, and then you look at its vertices and put them in the queue. And then you handle and then you update the ones as you go. Okay? And it's kind of cool how it actually looks exactly like the code for the breadth first search or the level order printing of a tree. Right? You enqueue the why did I have S there? Oh, for the vertex, you enqueue the vertex, and then you go through this loop, this while loop, and you dequeue the vertex, and then check all the adjacent vertices. You walk through it. Slightly better than the n squared one. Okay. Again, you don't need to know this, but you should know that when you're doing a breadth first search, you're going to use a queue. Okay. All right. Before we do this, I will prep this by saying this is one I was talking about that was the most probably the most well-known algorithm in all of computer science. Why don't we take a 2-minute break, 3-minute break, and come back. Shake yourself out, because this one's a little more intense. OK? Go. All right, let's get going. All right, you guys shaking out? Ready for this? OK. This algorithm is called Dijkstra's algorithm. It's by one of the most famous computer scientists in the world. Name is Edgar Dijkstra, I believe. It's one of the few people that has an IJK in his name, like in all three letters right there. He's like a giant in the computing field, right? He's been around doing computer stuff since like the 50s. And I believe, if I'm not mistaken, he actually still works in as a professor, I think the University of Texas, but I may be getting him mixed up with somebody else. But anyway, he came up with this algorithm that allows you to find the shortest path distance for weighted graphs. Okay, it's not the only one, but it's a darn good one, and it's kind of the classic algorithm. If you're ever going to get asked an algorithm like in an interview for graphs, they'll probably start with this one. Okay, and they might. It's a little like it's kind of intense, but you'll see how it works. Once you get it, it's not so bad. And what we'll do is we'll go over it today, and then I will let you go and ponder it for like the weekend, and then we'll come back on Monday, and we'll kind of we'll keep going. What did you say?
He died.
Oh, he died. All right, that's too bad. Well, anyway, great computer scientist. So Dijkstra's algorithm uses what we call is actually what we call a greedy algorithm. Okay, greedy means that it solves a problem in stages, but at each stage it says, what's the best thing for me to do right now? Right? It's greedy about it. It says, right now, I know the following things, and I'm going to do the one that's best for whatever like goal I'm achieving. Right? Now, greedy algorithms, sometimes they work great. Right? Sometimes they actually don't work. So I want to give you a little example of a greedy algorithm that sometimes works, and then when we change things a little bit, you'll see, oh, the greedy part doesn't work anymore. Just so you kind of have an idea. All right, more coins today. So anybody ever work in retail? You have to count out coins, right? Maybe not. Maybe you don't work in retail. But if you ever have to count out coins, right? If you're being nice, you'll count out coins in a greedy fashion. In other words, you'll try to count out the coins so that you get the least amount of coins to the person that you're giving change to. If you're like the person's been mean to you, you might like add a few extra pennies instead of a nickel, right? Right? You'll like try to do it not greedy. But if you want to do it greedy, you'll do the following algorithm kind of in your head to do this. You just count by the greatest coin first, and then you count the next greatest coin, and then you end with, when you finally get through the other coins, you end up with pennies, and that's how you count out the change. Right? So for 15 cents change, right, you can't use quarters, right? But you can use a dime and a nickel, and that's only 2 coins. Not bad. Right? You wouldn't want to do a dime and pennies, but you wouldn't do that using this algorithm, because the greedy algorithm says start with the biggest coin first, and then go down from there, and you will get the most amount of change, or the correct change, in the fewest amount of coins. OK. What if we added a different type of coin, like a 12-cent coin? What would you call a 12-cent coin? A 12er. I like that. I think I put that on the next page. I was thinking maybe a does. Call it a does or something. I don't know. But anyway, if you add a 12-cent coin, try to make 15 cents change using a greedy algorithm. What are you going to do? No, that's not the greedy algorithm. The greedy algorithm says count by the greatest coin first. So you can't do quarters, but you can do the does, or the 12er, right? And so you get a 12, and then all of a sudden you've got to skip nickels, because you can't put any nickels in there anymore. And now you have what's left? 3 pennies, right? So now you've got 4 coins, and you've missed the idea that you can still do it with a dime and a nickel. So then in that case, the greedy algorithm doesn't actually work. OK? So it's right there. Yeah, so I called it a 12er. Right? And you can see that sometimes these greedy algorithms don't work. The good news is Dijkstra's algorithm is greedy, and it always works. OK? Which is kind of cool. Well, it always works for positive weighted paths. We'll talk about negative ones in a little bit. All right, here's how it goes. Okay, what you do is stages, just like before, the unweighted one. But what it does is it selects a vertex. And it says which vertex to select. It's the one that has the smallest distance among all of the unknown vertices already. Okay? And then it says, I declare that the shortest path is now that path, this path to that vertex. Okay? And at each stage, it's still it decides whether or not it's a good idea to use a weight on a particular path based on this greediness algorithm. It says which one of you have not been known yet, and which one, and of those, who's the least one? Who's got the shortest path? OK, so that's how it works. And what happens is as you go through, we'll walk through it, and we'll see actually how it goes about doing its thing. OK, and it's as I say, a greedy algorithm. What we're going to do in this case, we're going to add a column to our table here. And this column is going to allow us to actually figure out what the shortest path is. Right? Because last time, remember how we said, oh, the shortest path from 3 to 7 is 4 or whatever. But did that tell us how to get there? Like, it would be a bad thing if you typed into Google, take me to New York City, and it said, it will take you 4 hours to get there. Good luck. Right? I mean, it doesn't tell you how to get there. It just says, hey, it's going to take you 4 hours. Right? Well, that doesn't help you much. It's nice to know how to get there. OK, so that's what this will allow you to do too. OK, same basic setup as before. OK, you have all these infinite paths of the ones you don't know. You've got one that we're going from. This time we're going to go from 1. OK, so we're going to go from vertex 1. And everybody is unknown at this point. OK, so the algorithm's right from the top, it goes ahead and it says, of the unknown ones, everybody, what's the one with the least distance? Vertex 1, because it's the only one that's there, right? OK, and by the way, it doesn't have any previous, so you could put a dash there too. But distance from, so you say, OK, what vertices are adjacent to v1? Well, we've got 2 and 4, and those are the only ones that are going from v1. OK, so it can update that, and it can say, OK, fine. The path from v1 to v2 is now how much? 2. It's not, you don't just add 1 anymore. It's 2, right? And the path to v4 is 1. OK, and so now you've taken care of vertex 1, so you mark it as known. OK, so there you go. You mark it as known. All right, what's the algorithm say? Of the unknown vertices, which one has the least distance? This one's known. So these are unknowns. The least distance is now 4. You better pick 4. And you look at 4, and you say, OK, which vertices are adjacent to 4? 4 is a good one because it actually goes to a lot of things, right? You've got 5 and 7 and 6 and 3. OK, so if we know the current distance to 4 is 1, what's the distance to 7? 5. And the distance to 6 is 9. And the distance to 3 is 3. And the distance to 5 is 3. So far, so good. And you put that in the table. OK? And you say, now I'm done with 4, and you're dead to me. Right? And we've updated all of those. OK? Of the remaining ones that are unknown, what's the least one? Which one is it? 2, right? Because of the ones that are unknown, this one's not known, not known, not known, not known, not known. 2 is the one with the least one, because this one's known and that one's known. So we go to 2. Then we look at 2. Same thing. We rinse and repeat, right? 2. Now, this one's a little interesting. OK? Because 4 is already known, is there a way to get to 4 that's less expensive than before? There's not going to be, actually. So you can actually ignore that one, right? Even though, and you could look at it and say, OK, well, it's not going to be less than, because it's 1 now, and now it's going to be 4 or 5 if I try to go there. But you're not going to update that one, OK? And especially because it's already known. All right. But then let's see, 5. 5 is not known yet, so you do have to look at it. But what would happen if we added 10 to 2? We'd get 12. Do we want to update 5? No. So we just leave 5 as 3. OK, and that's it. OK. All right. OK. And you don't change 4 because it's already known. OK. Of the remaining unknown ones, which one's the least? It's a tie. What do you do with ties? Pick. Doesn't really matter. Doesn't actually matter at all. Right? You'll always end up with the same result, as it turns out. But you pick either one. In this case, we'll pick 3. OK? You look at 3, And it's the same idea. 3 goes to 5 and 1. 1 is already known. Sorry, it goes to 6 and 1. 1 is already known. And 6, it would be, let's see, 3 goes from 3. 3 plus 5 is 8. And 6 is 9 now, so we do want to change that to 8, correct? OK, and we do that. And then we mark that one as known. Mark 3 as known. The other one that we could have chosen, which is the only one left to choose that's the least of the other ones, is 5. So you do 5. And 5, let's see, only goes to 7. And 5 starts out at 3. And 3 plus 6 is 9. Do we change 7? We do not. So we mark 5 as known. OK, and then let's see. We have to do 7 now. And 7 goes to 6. And 7 is 5. And 6 is 8. And so 7 plus 1 means, do we change 6? And by the way, I've been forgetting about telling you all this the whole time. This is just the last one you came from. So like right now, we're on 7. And we're about to change 6. So we'll not only change 6 to the value of 6, but we'll also change v3 to be coming from now v7. It's where it last came from. Make sense? Let's do that. OK. And finally, we only have one that's unknown, and it's 6. And the nice thing is 6 doesn't have any adjacent vertices to it. So all we do is mark it as known, and we are done. OK. All right. What's the shortest path distance from vertex 1 to vertex 5? 3. You can look at it right off the table, right? 1 to 5 is 3. All right, how do we get there? Yeah, how do you know where we get there? Watch this. Where did it come from? 4. Where did 4 come from? 1. And you're back to where you started. That's how you do it. So you just walk backwards through the list, right? Let's look for 6. 6, how did we get there? Well, we were at 7. And then from 7, we went back to 4. And then 4, we went to 1. Right? Oops, sorry, 4, we went back to 1. So you see how you can walk it backwards? That's actually a really easy algorithm. It's just a matter of doing just a quick little recursive back search, like through the vertices, right? You say for each print path, right? For some vertex, right? If the path is not a vertex, you print the is not equal to not a vertex, right? Meaning it's, let's see, what do I have for not a vertex? It's not equal to not a, that's a terrible way of phrasing that. But anyway, you basically print the print path, which is the recursive thing of that, and it will go back and print. It'll print it. It will print it in reverse. Right? Yeah. Is not a vertex what?
Vertex B.
Yeah, I think not a vertex, probably vertex B. Yeah. OK, questions on Dijkstra's algorithm? We will go over this again on Monday, because this is kind of an intense one. It's not that once you figure it out, you go, oh, I get it. Just simply go to the one that's unknown and what's the least one, and you go. But you should know how to do this, because I'll ask you a question about doing this on the final. OK? All right. So that's that. The one other thing I wanted to quickly show you was there's a program I downloaded called GraphT, T-E-A, right? And it's a Java program. It runs on all these different platforms. And what you can do is you can actually create graphs from it. And let's see. You want to do a directed or undirected graph? What's that? Undirected. OK, well, then an undirected graph. Not as fun, I don't think. But anyway, if you it's all right. Anyway, so you can do this. And then you can just connect them, right? And you can say 5 goes to there, and 5 goes to 2, and 5 might go to 4, and 1 goes to 0, and 2 goes to 3, and 3 goes to 1, and I don't know, 4 goes to 0. And now you've got this graph, and you can do fun things. Like you can say, OK, I don't actually want it up there. I want it down here. And it'll do it. And you can kind of manipulate that, right? What's cool is you can also, for each one, and I haven't figured out how to actually say, even though there's a little thing up here that says label, it says, let's see, where is it here? Oh, no, it's undirected. Wait a minute. Does it have, it doesn't have the actual, not only is it undirected, but it doesn't even allow you to put the amount in there either, which is too bad. But what it will do is you can do things like all these algorithms on it. It will do Dijkstra for you, but for this one it's not. Let's see what happens when I do Dijkstra. Dijkstra, if I select 5, did it work? Yep, play. There we go. Please choose a vertex. And then what it does is it actually walks you through the algorithm. You can go faster or slower. So you can see the algorithm in action, right? It will do, let me see, reports. It will give you, if you want the, where is it here? What's that? Well, yeah, I don't know what the chromatic number is. Something to do with the graph, the coloring of a graph. But you can actually do the, let's see. There's an adjacency matrix in here, which I found earlier. I don't know where it is now. Reports, let's see. No. No. Oh, spectrum of adjacency. I don't think that's what it is. Oh, there it is. Yeah, adjacency matrix. So it'll do an adjacency matrix for you, right? Which you can actually, if you, let's see. Oops. You can save it, or you can copy it, or whatever. So I'm just forgetting why it won't. Let me see. Why it won't let me do this one, but before I could figure out how to do it, but there it is, the adjacency matrix. There it is. So you can do that, and then you can copy it and whatever. So you can do all these things with it, and you can actually add weights to the directed one. I thought you could add weights to this one, but it doesn't look like you can. But I couldn't figure out how to print or show the actual weights on there, so that doesn't help. But it's kind of neat that you can play around with it. So go ahead and download it. It's free. It's for all the different platforms, and it's just a Java program, and you can run your various algorithms on it. Okay. All right. There's a lot of stuff for one day. Any questions on graphs, Dijkstra's algorithm, any other weighted path algorithms? OK, see you guys Monday.